Very good afternoon, all of you.
Good afternoon, sir.
Okay, screen is visible.
Yes, sir.
Okay, so in last lecture we have completed with unit number first. Okay, then second unit, that is design rules and layouts. Okay, that we are going to cover in the guest lecture. So probably we will plan guest lecture for unit number 2 in the maybe if possible next week. Okay, we will start with the next unit, that is unit number 3, combinational logic gates in CMOS. See, now in unit number first we have studied about the basics of MOS transistor theory, right? Then different CMOS, what is difference between BJT and MOS, then how what are the characteristics of CMOS, its different operating region, right? It has 5 operating regions. So all that part we have already studied in the first unit. Now, by using that, after understanding the CMOS, we are going to discuss some combinational logic gates using by using CMOS technology. So what are different points that we are going to cover under this? So static CMOS design, complementary CMOS, then implementation of Boolean expression using CMOS logic, then ratioed logic, then pass transistor logic, then dynamic CMOS design. In that, dynamic logic basic principle, then speed and power dissipation, different issues or problems that are associated with the dynamic design, then cascading dynamic gates, and comparison of the statics and dynamic design in CMOS. So these many points that we are going to cover under this unit. So before actually start with this unit, actually we have discussed this part before beginning of the first unit only, and it is a kind of prerequisite for this subject also. But then also in a very brief we will revise this. So first of all, we need to understand a clear difference between the combinational and sequential logic, right? So what do you mean by combinational and what do you mean by sequential logic? So this combinational logic means what? There is no involvement of any memory element. In combinational logic, there is no involvement of any memory element. That means what? There is no feedback path, right? And in case of sequential logic, what you can say? So sequential logic do involve some sort of memory element, right? Sequential logic does involve some sort of memory element. So that is a basic difference between the combinational logic and sequential logic. Now, as a part of our syllabus, we are going to different first the static CMOS, then in that complementary CMOS, ratioed logic, pass transistor logic, or transmission gate logic. And in dynamic CMOS, domino logic and NPMOS logic. So now what is static CMOS circuit? This is the first question that may come to your mind, that what do you mean by static CMOS circuit? So at every point in a time, at every point in a time, except during the switching of the transients, each gate output is connected to either VDD or VSS or low resistive path. VDD means the positive high voltage. VSS can be a ground zero or maybe a minus VDD. That means negative maximum voltage. That you know. The output of the gates assumes at all times the value of Boolean function implemented by the circuit. And in contrast with the dynamic circuit that relies on a temporary storage of signal value on the capacitance of high impedance circuit nodes. That means for or to whom you can say it's these are the static CMOS circuits. So these are some characteristics or specifications, right? For that you can say these are the static CMOS circuit. What is that? First, at every point, each gate output is connected to either VDD or ground or VSS. This is the first point. Second point, what you can say, the output of gates assume at all times the value of Boolean function, right? Different Boolean functions that we are using by using De Morgan's theorem and all that. So output of every gate at any time, it is a Boolean function. Means it is not any random or discrete value, right? And in contrast, a dynamic circuit relies on temporary storage of signal value on the capacitance of high impedance circuit nodes. So uh, dynamic circuit, as the name indicates, it is not a static one, it's a dynamic circuit, so that relies on a temporary storage of a signal value, right? In contrast with the static CMOS circuit. So to summarize this, first point you can say is at every point in a time, right? So output of each gate is connected to either VDD or VSS, it's a static circuit. Secondly, you can say at any point, at any time, the output of gates, right, for a static CMOS circuit. So output of gates assumes at all times it should be, or rather it is a value of Boolean function, right? So these two circuits you can say it's a, or these two circuits you can say that's are the static CMOS circuits. Now to analyze or to understand the function of any digital gate, which parameters that you should understand? First, its area and complexity that you must understand, then its performance, right? Then power consumption and reliability robustness and reliability. So you can say the robustness and reliability analysis is nothing but the static analysis, and the performance analysis is nothing but the dynamic analysis, that you can say in a general way. Now next point of our syllabus is a complementary CMOS. Okay, complementary CMOS. So you have studied the CMOS. What is CMOS? It has a pull-up network, right? It is of PMOS, right? That will act as a pull-up network, and pull-down network. That pull-down network is of NMOS only, and pull-up network is of PMOS only. So when you combine together in a parallel, that forms the CMOS, right? That forms the CMOS, complementary MOS. So now what is a what you can say the function of that pull-up network, which is made up of PMOS, and what is the function of that pull-down network, right, which is made up of NMOS, that you know. So PMOS has a capability to pass strong logic 1, right? PMOS has a capacity or capability to pass strong logic 1 and weak 0. And in case of NMOS has a capability to pass strong logic 0 and weak logic 1, right? So what we did, we have combinedly using PMOS as a pull-up network and NMOS as a pull-down network, so that the drawback of each other can be compensated, right? So the drawback of each other can be compensated, and in case or as a result, we are getting strong logic 1 from the PMOS and strong logic 0, that is from the NMOS, and that forms the CMOS. So all the pull-up networks, that is PUN, and pull downs are dual networks, right? Pull-up networks and pull-down networks are the dual networks. So first, before starting with the next part, we must understand that NMOS transistor in series or parallel connections. So what is result when you connect the NMOS transistors in series or a parallel fashion? So the transistor can be this transistor can be thought as a switch controlled by its gate signal. So as of you know, the this enhancement type that is we are going to discuss here also, the enhancement type are normally off transistors. Means what? These are these can be used as a switch. So this NMOS transistor, right, you can think doesn't irrespective whether it is a NMOS or PMOS, you can imagine it as a switch, right? And who controls or who decides when to on that switch or when to off that switch? It's the gate signal, right? Your gate signal decides when to on the switch and when to off the switch, right? So this NMOS switch closes when switch control input is high. That means what? If you provide high input towards the gate, the switch is on. That means it is in a conduction mode. And when you provide or when you apply a zero voltage, that means when you connect that gate towards zero, then nothing will happen. It will act as an open switch or disconnected circuit, right? So now first case, when you connect this NMOS transistors in series, right, you have a and B as an input, or sorry, A and B are the gate signals and X and Y are the input and output. So if X is equal to Y, if A and B both are is equal to 1. That means what? If both transistors are in a conduction, then and then only whatever is at the input side will pass towards the output side, right? Similarly, when you connect this transistor in a parallel fashion as shown in the second figure, okay, so this figure, it's a parallel fashion connection, it's a series fashion connection, okay. So this NMOS transistor, when you connect in this series fashion, then what happens? So X, and this is the output Y, okay. Then when this X will appear, or well, it will get transferred toward the output, then A or B, that means what? This any one of the transistor is on, then also the input will get travel to the output side. Input will get travel to the output side. म्हणजे काय? तर पॅरलल फॅशन मध्ये जर का एक जरी हा जरी क्लोज ओपन स्विच असला, म्हणजे काय, या गेटला तुम्ही 0 दिलत, पण बी ला किंवा व्हाईस वर्सा की एक ह्यातला कुठलाही एक एनमॉस जरी चालू असला तरी ते इनपुट आउटपुटला ट्रान्सफर होणार आहे. मीन्स व्हॉट? इट्स अ ए ऑर बी. Means parallel fashion of NMOS is nothing but the A or B, and series fashion of NMOS is nothing but the A and B. A and B, right? So you can say the series connection of NMOS, it is AB is equal to 1, then and then only input is equal to output. And in case of parallel connection, A plus B is equal to 1, then and then only input is equal to output. And as you know, NMOS passes strong 0 but weak 1. Okay, this is very important point. And to actually overcome the drawback of this NMOS and PMOS, right? PMOS has a capability to pass strong logic 1, weak logic 0, and NMOS has a capability to pass strong logic 0 but weak 1, right? So accordingly you have to take or you have to combine these two so that the overall drawback of each other can be compensated by each other only. So this is about the NMOS transistor, where it is connected in series or parallel fashion. Now you can say this. So when this Y is connected to ground, right? The second part, this Y is connected to the ground. Then what happens? Now, if suppose X is 0, X is 0. And if you switch on the both NMOS transistors, that means now you apply 1 here, then what happens? X will be the AB bar. That means it will invert, right? It will be the invert when you connect this Y to the ground, right? Similarly is the case with the parallel fashion. When you connect this Y to the ground, then it is a X is equal to AB bar, right? X is the AB bar because you have connected this to the ground. That means it is a 0, right? 0 output as it is used in the pull down network. So always this Y is connected to the ground. So it is AB bar. Now reverse is the case with the PMOS transistor, right? So we have discussed what we have discussed, the PMOS transistor in series, sorry, NMOS transistor in series and parallel fashion. Now here we are going to discuss the PMOS transistor in series and parallel connection. So this PMOS switches closes when switch control input is low. Why low? Because it has a bubble that indicates it's an inverter. That means when there is a 0 0 at the gate, then it will get converted to the 1, and then only the PMOS will be in the conduction mode, or it will close switch, or it will be the open switch. Now when this X is equal to Y, if A and B is equal to 0, right? This A and B is equal to 0, or in other case you can say, or in other case you can say A plus B bar is equal to 1. Why 1? As it's a PMOS, as it's a PMOS, that means inverter. So in case of both PMOS as well as NMOS, right? PMOS as well as NMOS. So whenever these are connected in series, it's a OR function, and whenever these are connected in parallel, so it's a sorry, whenever these are connected in series, it's a AND function, and whenever these are connected in parallel, it's a OR function, right? Series AND function and parallel OR function. Okay, so you have to remember in this manner. Similarly, in here also, in case of this parallel combination also, right? So when any one of the PMOS transistor, right, out of these two will be in a conduction, then X can reach towards the Y. That means now input can be go towards the output, right? If anyone is 0, that means it is in a conduction mode. So it's a nothing but OR function. A bar plus B bar is equal to 1. And as you know, the PMOS has a capability to transfer strong logic 1, but weak logic 0, right? Now, what happens when this Y is connected to the VDD, as it's a pull-up network, right? So always for in case of PMOS, it is always connected to the VDD. Now, if suppose this Y is connected to the VDD, and if X is equal to 1, then what happens? And if A and B both are 0, then this X is equal to A and B bar. A and B bar. And similarly, in this case also, if it is connected to the high voltage or a plus 5 voltage VDD, then it is A plus B bar. That means A bar or B bar, right? So in this manner, you can use this PMOS when it is this second terminal is connected to the VDD. Now this combined series of pull down network and parallel pull up network, or parallel pull down network and series pull up network to complete the logic design to output good 1 and logic 0, right? So it is depend. You can combine series pull down network and parallel pull up network, or parallel pull down network and series pull up network. That is depending upon what? The Boolean expression. what boolean expression and how you are actually going to implement it. So based on that, you can decide where to use the series of pull down network and parallel of pull up network, or where to use parallel of pull down network and series of pull up network, right? And you should get the good one as well as good zero, and not weak one and weak zero. Getting? So you have to remember this part. So next part is a complementary CMOS logic style construction. So by using this pull up network and pull down network, how we can actually implement different logical expressions using the CMOS network. That means the pull up and pull down network. Okay, so this part we will continue in the next lecture. Okay, for this time we will stop here. If you have any query or doubt, you can ask me right now.